Okay, it's 12:30, so let's get started here. Assignment number 2 is due September 23rd at noon. Today we will continue in the data steps section and maybe get into the macro section. Are there any questions before we begin? Okay, so I want you to turn to page 16 in the notes. So today we're going to spend a large portion of it discussing various functions that are available to you that you can use in a data step. We will begin with some simple functions that are meant to make your life easier by being able to summarize multiple variables at the same time. So if I go over here to SAS, let me make this bigger again. Hold on. Okay, so to illustrate some very simple functions, let's suppose I put together a very simple data set. In this data set, I'm simply going to enter it directly into SAS. I'm going to use the data line statement to help me do that. We've seen this before. There are going to be 3 variables, x1, x2, and x3. And so if I just enter that in, simply, I have basically 2 observations. And I just simply put 1, 2, 3, 4, 5, 6 there. Okay, so how about we look at, well, how could we sum across the variables? Very simple, as you might expect. If I, based upon my data set that I created, which I called set 1, create a new data set called set 2. If I want to just simply sum up the variables, I just take x1 plus x2 plus x3, as you might expect. And so now I've created a new variable called sum1. But there are 2 other ways that you can do this. For example, there is a function that allows you to sum up stuff. So if you just say sum parentheses x1, comma x2, comma x3, and parentheses, you get the sum of the 3 variables as well. Now lastly, there is one other way that you could do this. It's maybe a little bit more unfamiliar to you. And that is, again, using the sum function. But inside that, you say of x1 dash x3. Okay, so that dash there means 2. And you'll see this in not just in this particular function, but other functions, and actually in props, whenever you have to specify particular variables. If the variables have exactly the same name, except for numbers at the end, you can say something like x1 dash x3 to mean x1, x2, and x3. So it's a little bit of a shortcut that can be helpful when you're dealing with a lot of variables at the same time. Obviously here I only have 3, so it's not that big of a deal. Note though that you always need that of there if you're to do something like that. And so there's many other functions like that. You could also use the max. There's a min function too as well. And again, well, how can you find out about these functions? That's where you, on your own, should go take a look at the help of the functions that are available to you, and actually try some out. So in the notes on page 17, I give you the location of where to find all the SAS functions that are available to you. Take a look at the ABS function. What do you think ABS does? Well, absolute value. Okay, try it out. Make sure you can do it. You can use it. Now there's other functions too. Well, here's one other function, the square root function, SQRT. Kind of doesn't expect that. As a review from before, suppose I wanted x1 squared. So I take x1 SQ equal, and then what do you think I need to do after that to get x1 squared? Very good. x1 double asterisk 2. Okay, not the caret sign, as you would normally expect. So if I run that, you can see that indeed we are getting what we should be getting. So a simple test question might be, well, how do you get the square? That's one double asterisk 2, for example. Okay, so just very simple summary functions. Let's move on to the bottom page 17 then. Now we get to some more interesting ones when we're dealing with probability distributions. Okay. Statistical software packages have made the use of statistical tables obsolete. I haven't used a statistical table in a class for over 10 years, and I'm proud to say that. And so what we're going to do is look at some of the things that you would want to get out of a statistical table, but now using SAS to produce those numerical values. So if you notice here, it says see additional code first in blue. And in my SAS program that is on my website, I have inserted, oops, wrong program. I've inserted a little bit of additional SAS code right at this location. And what I'm going to do first is show how you can find a quantile from a standard normal distribution. Now just to make sure you understand what I mean by a quantile, let me draw a little plot. So let's see here. So here's my normal distribution. It is supposed to be symmetric despite how I'm drawing it. It is centered at mu. Now what I'm interested in first is the 0.975 quantile, meaning the area to the left of it underneath the normal distribution curve is 0.975. So in other words, I want this number there. The way that this is often denoted symbolically is by z, 0.975 if mu is equal to 0. Okay, is everyone clear what I'm looking for? So I'm looking for a quantile from a normal distribution. We'll take the standard normal here. And as I've mentioned before, as programming languages get older, there's going to be multiple ways to do exactly the same thing. And the first way that was, at least the first way I ever heard of how to do this, is to use the Probit function. Does anyone know why it's called Probit when we're dealing with a standard normal? That's okay. I didn't expect anyone to know it. But if you've ever heard of Probit Regression, Probit Regression basically uses a standard normal cumulative distribution function as a way to link the expected value of y to a linear combination of explanatory variables and parameters. And Probit stands for probability unit. Since people a long time ago used the normal distribution a lot more than we do now, but obviously it's still very important to us. Since it was such a standard thing, okay, if we're dealing with the normal, we have probability unit, Probit. Anyway, so if I say Probit, parentheses 0.975, Probit is a function. It will find a 0.975 quantile. Does anyone know what that numerical value is off the top of your head? Quick, do the integration. 1.96, thank you. Now a more newer way that came out later is using a quantile function. This is my preferred way to do it because I can use the quantile function actually with a whole bunch of other distributions. The key is I just need to specify what the distribution name is. So obviously with various distributions you have parameters that you have to worry about, and in this particular case you have the mean, you have the standard deviation. How do you know what parameters you have to put in there? Again, that's where the help is helpful. And of course I'm looking for the 0.975 quantile. So if I run this code and print it, so notice I'm creating a brand new data set to do this, I get the 1.96. Now let's say though, and now this actually goes into what's in the notes. Let's say though that you wanted to get the information about that probability, that 0.975, into the data step a different way. Here's how, and then I'll discuss shortly what the advantage of doing it this way could be in some situations. So, create a new data set. So notice I have set 1 here. I have set 1 above. So what's going to happen when I create this new data set? Just simply going to write over what was there previously. Just going to replace it. So I'm going to input a variable. So similar to what we've done in the past when we've created a new data set from reading in from a file, or if we're just simply using the data line statement to put some observations into a data set, I'm going to input area to left, for the lack of a better name. And wherever this area to the left, or whatever values I have for area to the left, I'm going to do some stuff on it. I'm going to find the quantiles, just like what we did above. Then data lines, 0.975. Now the one advantage of doing it this way is that, let's say, oops, I wanted a few more quantiles. Okay, so now if I do it this way and print it, now you can see it does the calculation on all the rows in that data set. Sometimes that might be helpful. Any questions? Okay. Okay, so if I have a quantile, so we know how to find a quantile. Suppose I give you a quantile. Yes?
That 0 and 1, is that mu and sigma?
Yes. Yeah. So you meant right here?
Yeah.
Yeah, that's mu and sigma. Let me just double check that. I am pretty sure it's sigma, not sigma squared. Obviously, if you take 1 squared, you get 1, so you get the same answer either way. Do I have it in the notes? No, I do not. So let's take a look at the help. So it's under base, functions, dictionary, quantile. Find normal. Okay, it is sigma. How do I know that? And you'll see this more in 883 if you haven't seen it in another class before you got here. Sigma is the scale parameter, so that's why I have scale there. And so that's why I know that. Also, if you take a look at, so it has a lambda there. Notice the lambda is there. And notice how lambda is represented in the normal distribution there. That's how I know that. As you probably have experienced elsewhere, the parameterization of probability distributions differs from one book to the next, and thus it differs from one software to the next. So you have to be very careful about what a particular parameter actually represents, and I think this is a good illustration of that. Okay. Any other questions? Okay, so we talked about if I give you a probability, I can compute a quantile. Suppose I give you a quantile, and now you need to compute a probability. Where's one place where this can be useful? Let's say if you're finding a p-value. So, as I said before, there's more than one way to do this kind of stuff. So, in this particular case, if I want a standard normal probability from a standard normal distribution, I can use prob norm, or I can use the CDF function. So I prefer the CDF function, CDF normal. Okay, I am basing it upon what I have for set 1 before. So we know that there is a variable called quant1 in there. So we'll put quant1 there. Mean 0, standard deviation of 1. If I run this, I'll get my corresponding probabilities, and I get the 0.975, the 0.95, and 0.9 back. So it just allows you to go the other direction. Okay. So let's see here, top of page 19. Let's say that I want to find the probability density value for the normal. So in other words, if let's say Z had a standard normal distribution, I want to know F of Z. I want to know what the height of the curve is at a particular value of Z. Well, there's a PDF function that allows you to do that. And so the Quantile, the PDF, and the CDF functions all work with a wide variety of distributions to get what you want. Again, do some exploring in the help, find your favorite probability distribution, because of course all of you should have a favorite probability distribution if you're a stat major, and see if you can get the corresponding probabilities or quantiles as you would expect. Okay? Okay, let's move on. Any questions? Now let's talk about how we can simulate a sample from a population characterized by a particular probability distribution. So let's say I want to simulate a sample, let's say a size 1,000 from a normal distribution. Why would that be of interest? Well, here are two main reasons why, and why being able to simulate data is such a fundamental part of being a statistician. First, to do statistical research. We are so very often wanting to evaluate how good a confidence interval is, how good a hypothesis test is under situations that we can control. And we want to evaluate, are we getting what we would expect? So for example, with confidence intervals, when I state I have 95% confidence that a parameter is between one number and the next, that confidence level, that's often what we refer to as statisticians as a stated level, because I'm stating it. You know, when we derive, let's say, a confidence interval for the population mean, you know, we have a 1 minus alpha times 100% level that we use in that derivation. But is that the actual level, or what I call the true, well, not just me, what people call the true confidence level? Some people call it the coverage level too. So even though you might state 95% confidence, guess what? It might not be that. It might be something else. It might be 90, might be 80, might be 99%, even though you state 95%. Does anyone know why that can occur? Let's talk about the very first confidence interval that you've ever seen before, most likely. A confidence interval for a population mean based upon a t-distribution. Could someone give me that formula? X bar excuse me? T what? The 1 minus alpha divided by 2 quantile from a t-distribution. How many degrees of freedom? Let's say the sample size is n. What? Yep, thank you. N minus 1. Then what? Standard error. Give me what the standard error is. S divided by square root of n. Thank you. So, that's a 95% confidence interval. Now, in the derivation of this interval, there's at least one important assumption that you have to make. Name that assumption. What? I'm sorry, I can't. Equal variances? Well, the population variance has to exist. But, we only have one population that we're sampling from. And so, yes, the variance has to exist. But what else? What's actually used in the deprivation? Exactly. You have a sample, x1 through xn, that's distributed normal with a mean mu variance sigma squared. Okay? If you don't have that assumption, you can't derive this interval. Okay? So that 95% confidence, if I use alpha 0.05, only exists when you have data from a normal distribution. How often do you have data exactly from a normal distribution? I've never known of taking a sample and known that I've had a normal distribution before. Perhaps you've been lucky enough and you have known that you've had a normal distribution. But I've never had that luck to do that. And so it might be of interest then to determine, well, if I don't have a normal distribution, how well is this going to perform? Is it really still 95%, or is it maybe something else? That's where what we do in statistics in terms of research comes in. Not just research, I mean just in terms of exploring certain things. Where let's say that instead my distribution is, for the x's is exponential. Okay, do I still get 95%? If I don't, how far off am I? Those are some important questions that we answer in statistics. That's, I think, unique then to our discipline. And so, how do we make these decisions? Well, depending upon the situation, you might be able to do some mathematical derivations, or you might be able to do what's called Monte Carlo simulation. We will examine how to do that shortly. Before we can do that, we need to figure out, well, how can we get SAS to generate a sample from a population characterized by a probability distribution? So that's what we're going to do next. Okay. So, to simulate one observation from a population characterized by a normal distribution, I can use a function in SAS called rand, or random, and it has a similar syntax to what we've seen with some of those other general functions. Here I put the probability distribution in, I put the corresponding parameters in as well, mu and sigma. And so if I run this, it's going to give me one data value, and then I'm going to print it. And I get negative 0.64437. Okay. What if I ran this exact same code again? Do you think I would get the exact same value? Why not? I am trying to randomly simulate values from a population characterized by this distribution. So if I keep on repeating this over and over again, as you might expect, I'm going to get different values. Now, generally speaking, you're going to get values between negative 1.96 and positive 1.96 about 95% of the time. You'd be more likely to get numbers closer to 0, to some respect, comparatively, I should say. So that actually causes a problem because let's say that I want to do I want to simulate one sample, and then maybe I'm going to turn off my computer, and then I'm going to restart doing what I was doing before, and I need to simulate a sample. Well, how can I reproduce the exact same sample that I was working on before? Well, it would be nice if you could. And so that's where it comes into play, where you can do what's called set a seed. So seed numbers, S-E-E-D, represent, it gives a pseudo-random number generator. That's basically what RAND that function is. It's a pseudo-random because nothing's ever fully random, because there's a computer algorithm behind this that's all doing this. It's, and maybe, I guess in the past in a computational statistics course you would learn about those algorithms. Now it's typically not as important. But anyway, what you need to understand is that you can specify a seed number, and this function RAND is going to use that information for that seed number to start the random number generation process. And every time you use that exact same seed number, you get the exact same sample. So that allows you to be able to reproduce your results from one running to the next, which is extremely useful. So how do we set a seed number in SAS? Well, we use what's called, which is new to us, something that's called a call routine. So call routines work similar to a function. The main difference is notice you don't see me put y equal either the call stream in it or just stream in itself. Call routines will not return to you an actual value that you can put in a data set. Instead, SAS sees that, okay, you want to call this routine here, and so I'm going to use the information like that for other calculations. In particular, the stream init allows me to set a seed number. In this case, I chose a number 7812. I could have chose a different number. But what SAS is going to do is use that 7812 to help initialize its random number generating process that is being used in RAND. And every time I use that exact same seed number, I will get exactly the same sample. So let me go ahead and do this. So now I got a value of negative 0.718. Let's run it again just to verify that I do get the exact same results in case you were doubting me. And I hope you weren't doubting me because, yes, indeed, I did get the same results. Okay? So it's extremely useful. So, one place where I use it, like in my research, when I do lots of Monte Carlo simulation studies, and I want to be able to reproduce that, from doing it one time to the next for a variety of different reasons, in addition to it just being good research practice, to be able to reproduce your own research. And so I always will set a seed number. It helps me, for example, when I teach. So if you'll notice in the notes that you do see negative 0.718, so you see exactly what's in the notes as what we did up here too. So it helps me in a teaching perspective. Okay, so why is it called stream init? Init means initialize. I am initializing, in this case, the random number generator. The stream, that's a term that's often used in this kind of a setting to mean what's actually being done is a stream of numbers are being generated to be used with the RAND function. And where it's going to start off with is 7812. Now, what's the actual connection between 7812 and negative 0.718? I know those numbers are, I guess, a little bit similar. That is more just by luck that happened. Just without understanding the actual algorithm that's doing the simulating, you're not going to be able to figure out what the connection is between that 7812 and the number that's actually generated. And to be honest, for most statisticians nowadays, it's not really worthwhile to understand that. Back when I was a student and we did have computational statistics courses, you would spend about half the time talking about how to generate random numbers. That sounds kind of boring, and that's why I never took the course when I was a student. Unfortunately, we typically don't teach that aspect, at least too much anymore. Okay. So again, I want to urge you to try some other distributions on your own. See what it gives you. Okay. Now we're going to talk about how we can simulate more than one observation. Because then this is where this gets useful. And then we'll be able to use that for a Monte Carlo simulation. Okay. So basically what I need to do is I need to repeat this process of using RAND a number of times. Let's say I want to take a sample size 1,000. So I need to repeat this 1,000 times. Well, remember before when we had a data set, when we had, let's say, a number of different things that you wanted to do after you, let's say, satisfy a particular condition with an if-then statement. You know, we used do, and then we did some stuff, and then we ended it. Well, that's essentially what we need to do here. So what I'm going to do is create a new data set called RANset3, for the lack of a better name. I'm going to initialize, I'm going to set a seed, and now I'm going to do. And I need to repeat it 1,000 times. And so this is where what's called a do loop comes in. You know, most of you who've had at least a little bit of experience programming in other languages, you've seen like do loops, you've seen maybe for loops or while loops or other kinds of loops like this. This is just SAS's way to do this. And do is the most prevalent one that's used in practice. So do, I'm going to set an index. I equal 1 to 1,000. So I'm going to repeat something 1,000 times. So and then notice where my end is. Notice how I nicely indent stuff so you can see what's inside the do loop too. So the first time through the loop, so when I is equal to 1, I'm going to simulate one number from a standard normal. And then look what I have, output. When have we used output before? Or what have we used it for? Create a new data set, putting information into a data set. Normally we would have output some kind of set. Okay? Here, since I don't have anything after it, where's the output going to go? Right there. So the first time through the loop, I equal 1, simulate one value from a standard normal, output it. Hits the end, comes back up, goes to I equal 2. Simulates a data value, outputs it, ends, goes back up, and does this all 1,000 times. So let's go ahead and run this. Print off the first 5 observations, and there you go. And again, every time I ran this, I would get exactly the same values because I set a seed number. Well, it's nice to have these 1,000 observations. It's going to be tough for us to look at all 1,000 observations at the same time. How about we do some stuff on it to verify then indeed that this did work? Something that's not in the notes. How about we find the mean and standard deviation? The mean should be about 0. The standard deviation of these 1,000 numbers should be about 1. So give me the code that I can use to find the mean and standard deviation. Proc means. Then what? Okay. And I want to be very specific here. I only want the output that I need. What should go after this? Mean? STD. Yeah. Then what? Var what? Okay. And indeed, we get about that. Okay. Here are some good stat-related questions. Suppose I were to increase my sample size. What do you think would happen, generally speaking, to the mean and standard deviation? Exactly. Why? Well, one way to put it is that X bar is it converges in probability to the mean parameter. Or another way to put it is that the X bar is a consistent estimator of the mean. And you can say similarly with respect to the standard deviation as well. Where would you first learn that kind of stuff? In Stat 883. If you didn't see it like in a course equivalent like Stat 463, a Math Stat 2 course for an undergraduate, or maybe somewhere else. So as n increases, you should get to where you're supposed to be. Mathematical theory says that, and we can demonstrate it with a computer as well. If you want, play with it on your own and see what happens. Also, just to verify that that we did get what we should be getting, how about we do a histogram? If I do a histogram, what should the general shape be of this data? Mound shape, symmetric, about 0, like a normal distribution. What's the procedure that we use? Well, proc SG plot. We've seen this before, but not with respect to histogram. So with proc SG plot, there is a statement called histogram X. So that gives you the histogram. But I want to go further. I want to actually superimpose a standard normal distribution on top of it. So that will help me see better that indeed this data looks like it comes from a population characterized by the standard normal. So the standard normal density, I'm going to do a density statement for X. I have some options, so I do the slash where I say what kind of distribution do I want put on it. So type equal normal. If I don't, I'm 95% confident of this. If I don't specify mu and sigma there, it will actually estimate it from the data. So we'll find the sample mean, find the sample standard deviation, draw a normal distribution, assuming the sample mean, sample standard deviation of the population versions. Here, since I do know that I simulated data from a normal mean mu variance, standard deviation sigma, I'm going to actually put those there. I have a nice little legend label to make it look nice. I think my battery might have went out. Hopefully not. And voila. Everything's matching up like it should. So that's nice. Okay, some comments then on page 22. Do note that that index there, actually becomes a variable in your data set. So you can actually see that variable if you actually look at the data set itself. There can be times when you're doing this where actually working with I inside that data set can be helpful. Unfortunately, I don't have a good example here to show you, but trust me, it can be helpful at times. Okay, now let's do this Monte Carlo simulation. So we're going to go back to talk about confidence interval for mu, the mean. And what we're going to do is examine, is 95%, if I state 95%, is that truly accurate if my data comes from a normal distribution? What do you think? Should it? Well, I'm satisfying the assumption. So generally speaking, it should. Let's verify that does indeed occur. So what I'm going to do is this. I'm going to simulate 1,000 data sets. I think it might be helpful to put the little blue part there, of size 10 each, just for clarification. So each data set is going to have a sample size of 10. Notice I'm not past that magical number of 30. But it's no big deal because, again, I'm simulating data from a normal distribution. So even if I have a sample size of 2, this should still work. Okay? For each data set, I'm going to calculate the confidence interval. So I have 1,000 confidence intervals. And what I'm going to do with each of the confidence intervals is check, is mu, which is 0 in this, going to be 0 in this case, is 0 inside the interval. And I'm going to count how often amongst these 1,000 data sets this occurs. What I'm hoping is this is about 95% of the time. This value that I get back, this proportion, you could say, the proportion of time that it worked for those 1,000 data sets, that a confidence interval captured the true mean, that's often referred to as the estimated true confidence level, or the estimated coverage. The reason why I don't call it just simply true coverage or true confidence level is because I'm using 1,000 data sets to estimate it. Okay? If I were somehow able to do an infinite number of data sets, then I could just say, yes, I do have the true value. Okay, so here's my code. So it's a little bit more complicated. This is done all the time in statistics. So I'm going to create a new data set called RANSET4 that's going to contain my 1,000 data sets of size 10. Initialize my seed, or I'm going to set a seed, I should say. And then I'm going to do nested do loops to get this to work. Let me remove this first to get it out of the way so it matches up the notes. So let's take a look at the inner do loop. That should look very familiar to us. It's essentially what I had just done previously, except for now I'm saying do n equal 1 to 10. So I have a sample size of 10. I'm going to use the rand function and output it. But remember, I want to repeat this 1,000 times, this whole process. So that's where this second do loop, this outer do loop, comes in. Is everyone comfortable with that? Silence means yes. Please move on. Okay. So I'm going to run it. I will print off the first 12 observations. And this is what we get. Here's the first data set right there, sample size of 10. Then the second data set. So when sim_num is 2, that's my second data set. So in total, how many observations do I have in this whole data set? 10,000. Or in SAS's terminology, a data set. Okay. Okay, next. What I need to do is actually calculate the confidence interval for each of those data sets. I need to do 1,000 confidence interval calculations. So, what do I need? We saw the formula before. You need the mean, you need the standard deviation, right? You need that t-distribution value, you need to know what your sample size is. Once you get all 4 of those things, you can calculate your confidence interval. So first, let's calculate means and standard deviations. Talk means. Data is in RANSET4. I just want the mean, I just want the standard deviation. The variable, x, that's where I stored all the normal values. Here's that by statement that we've seen before. My data is already sorted by sim number based upon how I simulated the data. So I don't need to run proc sort first. And then I want to output to a data set just the mean and standard deviation. And lastly, I don't need to see 1,000 means and 1,000 standard deviations come to my screen. So I'm going to use a new option I don't think we've seen before called Yoprint. So nothing goes to my results viewer. So notice there was nothing that went to the results viewer. We had what we had before. I come over here to my work library. Here are the 1,000 means and 1,000 standard deviations. So now it's just a matter of using a data set to do my rest of my calculations. So based upon outset 1, let's create a new data set called outset 2. My lower bound for my interval is that mean minus a quantile from the t-distribution, the 0.975 quantile, with 9 degrees of freedom. I take it times that standard deviation that I calculated, and then square root of the sample size. Do the same thing for the upper bound, but now I have a plus there. Okay? And then I have just one more thing left to do. I need to check, is my mean, which is 0, inside the interval or not? So let's say, come back over here, let's say my interval was this, 0.7 is less than mu, is less than, negative 0.7 is less than 0.3. Does this interval contain the mean, the true mean? Yes, it does. So in that case, I want to say, yes, it works. So notice that lower bound is less than 0. The upper bound, the lower bound is greater than 0. The upper bound of the interval is less than 0. So the reason why that's important to know is look at my code. The lower bound is less than 0. And if the upper bound is greater than 0, so in an if then, I want to create a new variable called check. That checks to see if mu is in there. Check 1 is equal to 1, where 1's a success. Let's say it worked. Else, check is equal to 0. Now notice I also have a check 2 and a check 3 there. That just shows you, you can see this on your own, that shows you other ways you could have done exactly what I just did. Okay? So if I run this code, go over to outset 2, let's take a look at the very first interval. Negative 1.26 to positive 0.07. Is 0 in the interval? Yes. Check 1 is equal to 1. So it gives me a logical check. Let me page down here. And there we go. So number 93, I guess there were some other ones up there too. Positive 0.023 to positive 0.75. Uh-oh, the interval missed 0. So therefore it did not work. Check 1 is equal to 0. And so if I sum up all those check 1 values, that tells me how many times out of 1,000 my interval worked. Or equivalently, or somewhat equivalently, suppose I just average all the 1s and 0s, I will get the proportion of times the interval worked. It contained the true mean by just simply averaging all those 1s and 0s. So how do we find an average or a mean? Proc means. So let's go ahead and do that. And what do you know? 0.956. Very close to 0.95. I'm satisfied with this. Yes, this interval is working as it should. So that's a Monte Carlo simulation. You'll do a lot of those in our program while you're here. Okay, let's move on to page 26. So some additional items. Every once in a while, you'll have the need to put a new observation in the data set. I'm sorry, not a new observation, a new variable in the data set that contains the observation number, or equivalently, what often occurs, the row number. How do you do that? Well, there is a particular trick in SAS. Use underscore n underscore. That's it. You can create sounds in SAS. In fact, I think I've heard like somebody like for some famous Christmas song, they've actually programmed it in SAS to play the song. I think that's for someone who obviously has too much time on their hands, but yes, I have seen that. When I've used sounds before is when I have a program that takes a long time to run, and maybe I want to go away from my computer for a while, but I want to be notified when it's done. I just have SAS play a sound. Take a look at my corresponding program. You'll see how to do that. There are also there are a number of time and date functions available. So this little data step here will find the current time and also the current date. So as you might expect, if I use a function called time, and also with it I have a function called minute, it extracts the minute from time. For some reason here, I didn't call this hour. I don't know why. It still works. That's what I did. Okay. Okay, we are just about out of time, but there's two more things I want to say. What I urge you to do, and I had hoped that we would be able to do this in class, I urge you to do is try this code with a different distribution. Now remember, the t distribution based confidence interval is derived assuming an underlying normal distribution. What if you used an exponential? What if you used a beta? Do you still get 95%? Excuse me. Maybe, maybe not. Try it out. Just realize that if you do try it out, you will need to change that part there to whatever your new mean is. So for example, if you use an exponential distribution, with the default in SAS is you use an exponential distribution with a parameter of 1. Well, what's the mean of that distribution? 1. So you need to change that zeros to 1s. Okay? If you use a beta distribution is really nice because it's very flexible. You have to think, well, what's the mean of a beta distribution? Well, if you have two parameters, A and B for that beta, it's A over A plus B. So you would just need to change that there. But try it, see what happens. Does anyone by chance know what will probably happen? Does anyone know what the word robust means in a statistical context? Okay. We use the term robust or robustness in statistics to represent a statistical procedure that still works pretty good, even if the underlying assumptions behind it are not there. And so the reason why this confidence interval for the population mean based upon a t-distribution is used so much is because it is robust to non-normality. So for example, I was trying some of this before class, just playing around with it. I use an exponential distribution. I didn't get 0.95. I got about 0.91 the one time that I ran it. So it still works pretty good. Not exactly like it should, or that we hope, but it still works pretty good. That's why this interval is so frequently used. There's another reason why this interval is so frequently used. What happens to the t-distribution as your sample size increases, if your degrees of freedom are like n-1? What happens to that t-distribution? It becomes closer and closer to the standard normal. Okay? Also, x bar, let's say the sample mean, there's a what you often learn about in your very first stat course, there's a particular theorem that's associated with x bar. Does anyone know what that theorem is? Central limit theorem. Okay? That as n goes to infinity, the distribution of x bar is going to become increasingly closer to a normal distribution. Okay. So if the t-distribution becomes closer to the normal distribution, which we know as n gets big, if the degrees of freedom are based upon the sample size, what happens then is that this confidence interval for a mean, once you get past that magical number of 30 for a sample size, that is more of a joke. We often teach, for example, n greater than 30, everything in your life is great. You can use normality. Well, what happens is that t-distribution becomes closer and closer to a normal. X bar itself has a normal distribution. The sample standard deviation, S, is going to come closer and closer to the true value of sigma. And so then this interval ends up working out very well because of the central limit theorem in those cases too. So some of that discussion is probably beyond what we need to worry about in this class right now. But the reason why I point that out is because you'll be seeing this as you go along in your other classes when you will be responsible for those kinds of comments. Okay. And then one last thing. Sorry. Here's a question for next time that I would like you to see if you can do on your own. And if you can't do it on your own, let me know. This was a question I was going to put it on an assignment, but unfortunately it didn't make it. I didn't want to overwhelm you with lots and lots and lots of problems. And that is, I want you in SAS to draw a standard normal distribution. How could you get SAS to draw one? I can do it using one data step, and then right after that, using proc SGPlot. There is a particular statement in proc SGPlot that I don't think we've seen before that will help you out. I think it begins with the letter S. That's my hint. Hopefully that will narrow it down when you look through the help. So try to do that on your own. If you can't do it, then please ask a question during our next class. Okay? If there's no questions, then that is it for today.